This is Neil with Anabit, and in this video we're going to cover how to make resistance measurements with an analog to digital converter, or ADC. And in fact, we're going to look at two different methods or circuit designs where we can make precision resistance measurements with an ADC. Check out anabit.co, where you can find open source reference designs of data converters such as analog to digital converters and digital to analog converters, complete with in-depth tutorials to help you get up and running quickly. The two different methods or circuit designs we're going to look at for measuring resistance with an ADC is first the voltage divider approach and the current source approach. So each one of these approaches will give an overview of the circuit, we'll talk about some of their best practices, and we'll also talk about some of their downsides. And then for current source approach, we're going to go in a little bit more detail. We're going to use Anabit's open source precision multimeter to do a demo that shows one of the best practices in action. And then we'll finish off by talking about how you would design a current source for that approach and where you can find more information on current source designs. Okay, let's start with the voltage divider approach. And as the name implies, we're using a voltage divider, right? So a lot of times you can use a voltage divider to divide down a voltage, which is essentially what we're doing. But here, we know the voltage, we know one of the resistances. We're going to make a voltage measurement to calculate the other resistance. So if you look at the circuit diagram, we have our pris, which is our precision. That's the resistor we know, the precision resistor that we know its value. Our mej is the resistance that we don't know. That's the unknown resistance. The ref is the voltage source value that we know. And then, of course, we have a buffer op amp and an analog to digital converter. And the reason we want the buffer op amp before the analog to digital converter is because by nature, op amps have a differential input. And so we want to make sure we're connecting two different leads across the unknown resistance, just measuring what we want to measure or the resistance we want to measure, and not signal paths to ground or anything like that. So that's one of the reasons we have the buffer amp. We also have it there because we want to get a precision buffer amp that has a high input impedance or a low bias current specification. So that makes sure that the measurement circuit is not affecting the actual voltage across the resistance we're trying to measure. And for the reference voltage, we want this to be a voltage value that we know, and it should be very accurate and stable. A good approach is to use the same reference voltage that the ADC is using, right? So an ADC needs a reference voltage to know its range. It defines the ADC's range. If we use the same reference voltage across the voltage divider, that means if there's any error in the reference voltage, or if it drifts a little bit, they're both drifting the same, the ADC's reference voltage as well as the voltage divider circuit's reference voltage. So that cancels out any of the error in the reference voltage, which is nice. If we look at the math above, we just basically take our voltage divider formula that a lot of people should be familiar with, where RM is our mej and RP is our precision. And so we just kind of flip it around, do some algebra, and we can see our mej equals our precision, which we know, times the measured voltage divided by the reference voltage minus the measurement voltage, and that gives us our unknown resistance. Real straightforward, especially if you're familiar with voltage dividers already. Now, some of the downsides to this approach are it's not great for measuring low resistances. If we're measuring high resistances, kiloohms or mega ohms, this is great. Why? Because any voltage drop between the connections of the resistors or traces on a PCB or anything like that doesn't really have much effect because it's going to be really low in the measurement or have very little effect on the measurement. But if we're measuring a low resistance value like 500 milliohms or 1 ohm or 5 ohms or 10 ohms, then all of a sudden you're going to have voltage drop in between your resistors that's parasitic, that you're not accounting for in your measurement, and that is really hard to account for in your measurement. Another downside is if you're trying to design your own multimeter, for instance, and you want to measure a wide range of resistances, this method could be tough because to ensure you're getting good accuracy across your different resistance measurements or ranges, you probably need to switch in and out different R precision values. And precision resistors, along with switches and things like that, are not cheap, and they add cost and size to the design. So easy setup to measure resistance, but be aware of those drawbacks. Okay, let's look at the current source approach. So in this approach, we use a current source instead of a voltage divider. And what's nice about a current source is current is common in a closed loop. So as long as we have our current flowing in a closed loop through our unknown resistance, we don't have to worry about any drop of voltage across that path the current is flowing, because current is common, right? So we have our known current source. We measure the voltage drop across the unknown resistance. We're using the same buffer amp and ADC for the same reasons, right? We want to connect across the resistance we're trying to measure and not other signal path elements. And then we want that high input impedance because we don't want our current flowing into our amplifier or our ADC. We want it flowing through the resistance. Anywhere else the current flows adds error to the measurement. Now, this method is what typically is used by multimeters or digital multimeters or DMM. So this is the method they typically use. And the way they handle different resistance values, because we talked about this being a drawback of the other method, is they just change the current source. So they'll change the current source value depending on the range of resistances you want to measure. And setting the right current source is important here because we want a current source that creates enough of a voltage drop to measure it, but we don't want a current source that has so much current that's going to start to heat up the unknown resistance, because when you heat up a material, its resistance changes, its resistance goes up. So we don't want our measurement method to change the value of the resistance we're trying to measure. If we use a low value current, then we're going to get a low voltage drop across our unknown resistance, which is harder to measure, right? You're not using the full range or resolution of the ADC, and lower voltage values always are more susceptible to noise. So we sort of have this trade-off between the current source self-heating, and of course higher current sources are harder to design, as well as then with the voltage range. So typically what you do to handle that is you're going to have a low current source value so you don't get self-heating, and then you're going to add gain to your buffer amp stage. So we're going to look at a demo to see that in action, to see how having that better voltage range match for your ADC contributes to more accurate resistance measurements. But before we do that, I want to mention the 2-wire versus 4-wire. So in this setup, I'm showing a 4-wire setup. And that means we have 4 wires, right? We have current source plus and minus. So those are separate connections to our resistance that we're trying to measure. And then we have our measurement connections right across the resistance. So those are 3 and 4. So we have 4 different wires making this measurement. Another way you can do this is you can do 2 wires where the measurement and the current source are both connected to the same line, whether that's a PCB trace or a cable, to the unknown resistance. And in this case, the current source and the measurement path are sharing some of that same path. And so you get a little more error because you're measuring the voltage drop over the area that the measurement leads and the current source share. So the 4-wire way is the best way to get accuracy because it eliminates, any of the resistance in the path of the current source and the measurement source. And this is similar to the last method we looked at, is if you're measuring high resistances, 2 wires is probably fine because the error is going to be so low. But if you're measuring lower resistance or you need very accurate resistance, 4-wire is the way to go. Okay, so next we're going to look at a demo with this method in action and showing how increasing the gain of a precision op amp leads to more accuracy in the resistance measurement. And then we're going to look at a quick slide that shows an example design of a current source that you could use in this circuit. Okay, so here we're looking at Anabit's precision multimeter open source design right here. We're looking at it from its side, and we're using a OG Arduino board, the Arduino Uno. This is the resistance we're measuring. So I chose a low resistance to kind of show one of the benefits of this method. So this resistance is about 5 ohms right here. And you can see we're using a 4-wire method. We have 2 wires connected to the resistor that connect to this screw terminal. So this is our current source. And then we have our measurement connections right here as these alligator clips. So we're doing a 4-wire resistance measurement on a low resistance value of 5 ohms. So I'm going to zoom in there, and then here, I'm going to show the measurements on my serial terminal. So I'm going to pause it. Wait, I'm going to let some fresh measurements show, then I'm going to pause it. So let's let some fresh measurement values come across. Let's pause it right there. So I'm printing out my settings, right? So right now my amplifier has a gain of 1. So no gain on the amplifier. My current source is set to 3 milliamps. So that's what my current source is set to. And then the voltage measurement I'm getting is about 15 millivolts, which is what we would expect for a nominal value of 5 ohms, right? So 15 milliohms would be perfect 5 ohms, but of course our resistance isn't perfect, so we're getting something close to 15 millivolts. So then when we do the math and we basically divide this by the current, we get our measured resistance in ohms. So it's 4.96, which makes sense, right? We should have about 5 ohms. So we do this again, you can see our value is very close. So this is nice and we're getting a good measurement, but we're barely using our ADC's range. Our ADC has a range of 2.5 volts to negative 2.5 volts. And we're only using 14 or 15 millivolts for this measurement. So we're not using much of our ADC range, which means our measurement is susceptible to noise and quantization error. So let's do another measurement where we increase the precision amplifier's gain to get a higher voltage value. Okay, I just loaded new code, which has a 32 gain setting on the amplifier. So let's print out some measurement readings and let's pause it right there. So everything's the same here, except we change the gain on our amplifier, which sort of changes our calculation a bit. But we have our 3 milliamps current source. Our op-amp gain is now 32, and so our measured voltage is much higher. Now, we're not covering the full range of the ADC, but we're covering at least 1/5 of it now with our measured voltage. So we're going to get better resolution. We'll get less noise on the low parts of that measurement. So then when we do our math and we take into account the 32 gain setting of the op-amp, we're now getting 4.93, which before we were getting 4.96. So how do we know that that is more accurate? And we can see it's pretty repeatable, right? 9328, 9327, 9327 right down here. So here is an image of making a 4-wire measurement using my $1,000 DMM. And we can see that the value is much closer to the second value we measured with the precision multimeter, which we're getting 4.933. So they're only off, or they're only different by maybe a couple hundred micro ohms, whereas the last one we measured was 4.96. So that was off by tens of milliohms. So you can see just by adding that 32 gain using a precision op-amp, it's very important that we mention that it's a precision op-amp, to get more of that ADC range, so we kind of reduce noise effects, we reduce any sort of low offset voltage error, as well as quantization error. Okay, then finally, I wanted to conclude this video by just showing a sample current source, because the second method looks easy when I showed it on the slide, because I just kind of show this current source existing. But the voltage divider approach is a little easier to implement because it's easier to get reference voltages, it's easier to get a known resistance than it is to create a current source circuit. So here's an example of one that basically what it does is it uses this MOSFET as a variable amplifier. So this basically is crowbarred into the previous picture, but instead of showing just a current source input, I have a voltage value along with this DAC input. So this is coming from a DAC, a digital to analog converter. We have this precision op-amp, and it's driving an N-channel MOSFET. And what happens is this amplifier is going to drive the MOSFET so that the DAC input voltage matches the voltage drop across the sense resistor. So by controlling the voltage drop across the sense resistor, we ensure that we have a continuous current flowing through the sense resistor. And since this is a closed path for current to flow, we're going to get the same current value through the unknown resistance, right? So you can see that, implementing a current source is not trivial. Now, there's other options for current sources. You could buy some of them off the shelf as ICs. You can also convert a linear regulator to a current source as well. I'll provide a link to another video that shows 2 different methods for making current sources. One is this method I'm showing here, and one is using a linear regulator. And of course, that video is going to go more in depth. Okay, that's it for how to make resistance measurements with an analog to digital converter. If you have any questions, please use the comment section below, or if you have any insights to add based on your experience with resistance measurements or anything you think I missed, please use the comment section. Thank you for watching.